This is another example of propped cantilever beam using consistent deformation method. Here we will consider the loading on the beam as triangular load. So the question is given as analyze the propped cantilever beam using consistent deformation method using consistent deformation method and draw shear force diagram, bending moment diagram, and elastic curve, and EI is constant. So here we have a propped cantilever beam of span 6 meters on which a triangular load is acting with an intensity of 20 kilonewton per meter, and EI is given as constant. Let us take this support as A and this support as B. So we know the consistent deformation equation is given as deflection due to load plus deflection due to prop is equal to total settlement of supports, and deflection can be written as area of bending moment diagram divided by flexural rigidity multiplied by centroidal distance. So here we can divide the propped cantilever beam into two simpler cantilever beams as one cantilever beam with triangular load. The load is acting towards the member and the intensity is 20 kilonewton per meter with points A and B span being 6 meters. And another will be a cantilever beam with prop, which I will take as reaction at B. So we have a roller support here, so there will be a vertical reaction which is taken as RB, and the span is given as 6 meters. Now the bending moment diagram for cantilever with triangular load will be a parabolic variation, but it will be a cubic parabola. So this will be a cubic parabola, and this will be a hogging bending moment, and the bending moment value here will be area of the triangular load, that is half into base into height multiplied by the distance between the centroid and the fixed support. So that distance is given as 1/3 of base. Okay, this is equal to 120 kilonewton meter. This is point A, point B, and 6 meters. And similarly for cantilever beam with prop, there'll be a sagging bending moment like this, and the bending moment at point A is given as 6 times RB, right? And the centroids for these bending moment diagrams will be shown like this, and the centroidal distance is taken from the centroid till the prop. This will be the centroidal distance. Now we have two bending moment diagrams, so we can apply our consistent deformation equation. Now before that, we need to know what will be the area of this bending moment diagram and the centroidal distances. So here it has to be noted, when you have a geometric shape of this fashion, this being a cubic parabola, the area is given as 1/4 of base into height, this being the base and this being the height, and the centroidal distances will be these distances. I can take this as x1 and the other one as x2. So here the shorter centroidal distance x1 is given as 1/5 of base, and the longer centroidal distance is given as 4/5 of the base. So this formula has to be remembered whenever we are dealing with triangular loads. So using these formulas, we can now write the consistent deformation equation for these two BMDs. So here for the first BMD, we have area of BMD as, since it is hogging BMD, it is minus 1/4 base into height. This is the area of BMD divided by EI, and the centroidal distance will be 4/5 of base, which is 6 meters. That is for the first BMD. The area is 1/4 base into height, that is 1/4 6 into 120, and the longer centroidal distance is 4/5 of base. So we get this equation. This is the area of BMD and this is the centroidal distance, and we are taking negative sign because it is hogging BMD. And to this we have to add the area of the second BMD multiplied by its centroidal distance. So here the area is half base into height, and the centroidal distance will be 2/3 of base, and this distance is 6 meters. So this will be plus half into base into height divided by EI multiplied by centroidal distance, which is 2/3 of 6. This will be equal to the total settlement, and there is no settlement of supports mentioned in the question, so the total settlement can be taken as 0. So here the only unknown is reaction at B. If we solve this equation, we get minus 864 divided by EI plus 72 RB divided by EI is equal to 0. So I can take EI to the right hand side, which gets cancelled, and from this equation I can determine the value of RB, which is calculated as 12 kilonewtons, right? So now we have a propped cantilever beam with reaction at B as 12 kilonewtons, and there is a triangular load. There is a triangular load of 12 kilonewton per meter. This is point A and this is point B, and this is 6 meters. And because there is a fixed support at point A, we will have a vertical reaction here. So let us take this as reaction at A. Now to calculate reaction at A, we can make use of the equilibrium equation. Sum of all vertical forces is equal to 0. So if I apply this, I will get RA plus RB is equal to, this load is acting downwards, and the intensity of that load will be the area of the triangular load. Okay, that is equal to half into base into height. So this is 20 kilonewtons. Half into base into height, that is 20. And I know RB is equal to 12 kilonewtons. So I can simplify this equation and calculate RA, which is found to be 48 kilonewtons. This is my reaction at A. So reaction at A is 48 kilonewtons. So I know reaction at A and reaction at B. So I can now write shear force diagram in kilonewtons. So the shear force diagram is drawn from left to right, considering upward forces as positive and downward forces as negative. So here at A, there is an upward force of 48 kilonewtons. So this will be 48. And from A to B, there is a downward triangular load of 20 kilonewton per meter. So it will be 48 minus area of this triangular load, that is half into 6 into 20. So that will be 12 kilonewtons. So minus 12 kilonewtons, this will be minus 12. And at point B, there is an upward force of 12 kilonewtons. So this becomes 0. Now, because this is a triangular load, the variation of the shear force diagram will be a parabola like this. It will not be a linear variation. It is going to be a second degree parabola. Okay. Now our job is to calculate the point where the shear force is 0, because we know wherever the shear force is 0, at that point the bending moment will be maximum. So let us consider this point at a distance x from point B. So this is point A, this is point B. So at this section, let me call it as section 1, 1. This distance is taken as x. So I know at this section 1, 1, the shear force is 0. So I can say shear force at section 1, 1 is equal to 0. Now, if I write the total shear force at this section by considering either right hand side or left hand side, this will be nothing but, if I consider on the right side of the section, I have 12 kilonewtons upwards, and this region of triangular load which is acting downwards, so it will be minus half into x into, now this height is taken as y, so here this will be half into base into height, that is y. Now the question is, how do we calculate this y? That is calculated by using similar triangles. So I have a big triangle here with base 6 meters and height 20, and I have a small triangle here with base as x and height as y. So using similar triangles, I can write 20 divided by 6 is equal to y divided by x, y divided by x. So from this equation, I get y as 3.33x. Okay, so now this equation is equated to 0. So now this becomes 12 minus 1 by 2 into x into y is calculated as 3.33x. 3.33x is equal to 0. If I solve this equation, I will get the value of x as 2.68 meters. Okay, so what it means is, at a distance of x equal to 2.68 meters from B, the shear force is 0, and at this point the bending moment will be maximum, right? So now to draw BMD, we have to calculate bending moment at various points, and the sign convention we use is sagging bending moments are positive. So sagging bending moments are positive. So now we know at prop the bending moment will be 0 because it is an end support. So bending moment at B is equal to 0, and bending moment at A will be. So I will consider a section at A. I will consider bending moments at the right side. So if I consider right hand side, so this will be 12 into 6, which is sagging. So it is 12 into 6. And due to the triangular load, this will be a hogging moment. So it will be minus half into 6 into 20 multiplied by the distance from the centroid till the point A, that is 1/3 of 6. So this moment will be minus 48 kilonewton meter. And also we know at this section the bending moment has to be maximum. So I can write bending moment at section 1 can be calculated. So this is my section 1. At this section I have to calculate bending moment, and I know x is equal to 2.68 meters. Okay, so at this section, if I consider right hand side, it will be 12 into 2.68, which will be sagging. 12 into 2.68, and this triangular load will cause a hogging moment, so it will be minus half into 2.68 into, now this height Y is 3.33 times X, that is 3.33 into 2.68, that is half base into height, multiplied by the centroidal distance, that will be from the centroid till this section, this much distance, that will be 1/3 of 2.68. So this moment will be 21.48 kilonewton meter. So now we have bending moment at various points. So we can draw the BMD in kilonewton meter. So this is our reference. Bending moment at B is 0. Bending moment at A is -40. So say this point is 40. And the bending moment here is going to be 21.48 at this section. So that is at 2.68 meters from point B. It's going to be 21.48, and then you join these points using a parabola. So below the reference is negative, above the reference is positive, and this point is the point of contraflexure where the bending moment is 0. So if required, the point of contraflexure can be located by considering the distance as say x1 from point B and writing an equation for moment at this point and differentiating it with respect to x and equating it to 0. So just like how it has been done in the previous examples, similarly the point of contraflexure here can be calculated. And the last part is elastic curve. This is the propped cantilever. So this portion is hogging and the remaining portion is sagging. This will be the elastic curve.